a collaboration is more than a set of parts. So you can actually do more together than you could just do one by one. And this is very true. This is very true. And I personally believe in this. And this is the reason why cryptographic is actually on the web. Probably I pushed the GIF just yesterday. So I actually work on this regularly, and everything is on the internet. So I'm actually running in a certain way against myself, because anybody can download the source code, and they can just change something and publish it into the competition. I'm actually looking forward to that. So cryptographic winning against cryptographic, because I think it's quite interesting to have something of a code base that everybody can work on. So I all ask you and encourage you to come around and have a look and work on this, because I think it's a great project, and we can really make a difference. So that's cryptographic, and that's what we're going to be using, of course, because I know best this piece of set solver. But anything could be used. Anything could be used. But this is the stuff I use. So I'm going to demonstrate now. We're going to generate a high-tech 2 problem. Well, actually, before that, I'm going to show you just a couple of three-dimensional and two-dimensional visualizations of what we're going to solve. Then we're going to generate a high-tech 2 problem. We're going to solve it with cryptographic, and then we're going to try to analyze this result. So, let's see. All right. Let's have some fun. All right. Well, this is actually a three-dimensional visualization of all those clauses that I told you. You know, those things that were clause 1, clause 2, clause 3. What they're sort of connected, right? Is there variables that are connected. Here, the dots you see are the variables. You know, as many dots as you see here, they're all the variables. And they're connected with those clauses. You know, they're connected with A or B. You know, and there was another bracket, or B or not C, and there was another bracket, or C or not D, etc. So those are connected, right? And so I'm just going to plot this thing and show you around. This is actually an adder, a binary adder. So we're adding, I think it's like a couple of bit adder, maybe 4 or 5 bit, maybe an 8 bit. So we're adding these kind of things together, and there's an input, of course, the values A and B, and then there's an output C. But of course, A and B are represented in multiple bits. In this case, for instance, 8 bits. So each of them are 8 bit, and there's an output, an 8 bit output, plus probably a carry out as well. So yeah, this is simple. So let's move on. Yeah. Well. Alright, so this is going to be a high-tech 2 instance. The same thing, right? So you have the variables, and they're all connected. Well, okay, so the red things you see here, the red things is, I can rotate this around, but it doesn't really make much of a difference. You see, it's a big, I don't know what it is. And you see those red things sticking out? That's actually the output there. So it does make some sense. So I actually generated 48 bits of output here, and there's 48 little red sticks sticking out. And those things inside, it's probably the state. So there's like a big state, you know, the 48 bits that I talked about. Well, that's inside. Those things are representing the filter bits and the state bits. It doesn't make much sense, but sometimes it makes a lot of sense actually. I can show you maybe something fun. Yay. Okay, so this is like a big cube there. That's SHA1. So this is like the hash function, you know. This is really cool, I think, because there's I believe this is the input here, and there's the output there, and it's sort of if you remember, it's like a rotating function. It's like rotating and rotating and mixing and mixing and mixing. At the very end, there's something coming out. And that's what it's doing. It's like there's the input, and it's like mixing, and there's the output at the end. So it sometimes makes a lot of sense. In this case, for Hightech 2, you can observe the output bits. You can probably, if you go inside, you might be able to observe some of the stuff that's going on. All right. So, by the way, before anybody asks, all of this is Git, right? You see there. Everything is up on Git. So I don't have much secrets around here. Everything is up on Gitorius, from Cryptomesa to the stuff that you just saw, the three-dimensional visualization, to the generation of Hightech 2 instances, all of that. Yeah, you can just go on, have a look, fun, play around with it, improve it as you like. So we need to generate this. We're going to download. Well, basically, you have to download this piece of software called grain of salt. Then I say I'm going to use Hightech 2 here. Then I'm going to give 40 bits of output. I'm going to guess 13 bits. I'm going to play around with it a little bit, and I'm going to output exactly one problem. Okay, so it's output, and it's going to be here. So if all goes well, I can solve this with cryptographic. Yeah. Okay, so it's doing it. These are the. This is the number of conflicts we're having. So it's 69,087. You see, it's going up. There's some optimizations we're doing in the middle. And then we do again a couple of conflicts, and then again optimization. It's like a sort of a cycle. We try to do this kind of search that you saw, and then we do some optimizations that you can easily read from set papers, or you can just read the code. I prefer reading the code, but some people prefer to have these fancy names for the stuff. I don't like fancy names, I just like code. But it's all, it all depends on who you're talking to. So this is a set of statistics that we see here, and at the very bottom it says unsatisfiable, which means we must have guessed bits wrongly. We guessed 13 bits wrongly, so there's a pretty high chance, 1 in 8,000 approximately, that we actually don't have unsatisfiable, and we have something called satisfiable, so it gives me the key. It just gives me a printout of the key. Very simple. But in this case, it doesn't actually give me the key because I guessed it wrongly. What's interesting here is that it actually took me 20 seconds on this really old piece of equipment that I have here. And imagine having a Core i7, some hyper-threading, maybe with the new crypto mini set. Yeah, that can be pretty fast. This is 20 seconds, so if you multiply around and divide and stuff, it's going to be about 2 days. So if you do 2 to the power of 13 solvings, because naturally I guess 13 bits, right? So there's the chance of hitting the right one is 1 over 2 to the power of 13. So I'll have to do this 8,000 times. So if you multiply this by 8,000, then you divide by, I don't know, 3,600 approximately, and then you get a couple of hours, and that's going to be about 48 hours to actually do this. So on this machine with single-threaded solving, with a 4-core Core i7, this is going to go way down. So it's just going to be a couple of hours, and you're done with Hightech 2. And that's a car. Yeah, but you don't really need your computer because you're just going to buy Amazon Cloud, right? And that's the end of that. What I like most about all of this is that it's all automatic. So you don't really need to do much. What you really need to think about is how to describe that piece of hardware that you saw up there in equations. And then from the equations, you go down to the description that I just saw, like was A or B and B or not C and stuff like that. And then it's all done. The fun part is that everything is automatized. So you go on my webpage, you download everything. It's all there. So from the description you describe your problem, your cryptographic problem in the way it was originally described in the paper that described it. So it's like the most trivial way of doing it. It's a text file that you just write down the equations, and then this thing will do this automatically everything. So you just alter, but not only that, modify the stat file, then you run crypto minisat on it, and it's all done. So you don't really need to be an expert. the expert part comes in when you really need to, you really want to crack a car, because you don't actually get this kind of equation set. It's a bit more complicated than this, of course. But the interesting part here is that this has been used for such a long time, and nobody really took notice. So these cars and the system in London, that's been implemented a couple of years ago. They could have easily asked me if that was secure, but of course they didn't. And it's quite interesting to see that the big industry is just taking notice. It's starting to take notice that it's not going to work out if you make your own little cipher and don't ask anyone about it and try to keep it secret, because eventually it will not be secret, at which point it will be broken, either by me or by someone else. It just takes time, effort. I was actually in France when I was doing most of this work. So I was paid by France actually, because I was in Institut National de Recherche Informatique et Automatisation, so in RIA, if you know. So let's get back here. Okay, so with all this three-dimensional stuff, actually there's one more thing I might be able to show you. This is not my work, but it is so awesome. I cannot not tell you. So, if you remember that thing with all the things that you remember that three-dimensional stuff with all the output bits sticking around? Well, that's high-tech too, as I explained. And this thing is actually showing that three-dimensional stuff while we're solving it. So basically, all those red things, my computer is too fast, apparently, or crypto minis are just too fast, or something in between. But what's happening here is that you're actually drawing the graph. So it's drawing a graph, and when we see that the red things are disappearing, that's because it was going back in the search tree. So it's going down in the search tree, it's picking all those variables and going all the way down, and then when it reaches a conflict, something doesn't work out, it goes back. You see sometimes it's actually almost everything is red, that's because it's almost found a solution, but at the very end it was like, it's wrong, so it has to go back. It's pretty awesome on bigger problems, and you can actually see it starting from for instance, you saw that big thing, and then it starts it here at the top, and then it goes down, 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 and then at some point it says, oh, it's not good, so it goes back, 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 and then go down. It's pretty awesome to see how it actually works out in 3 dimensions, and you're not just looking at the numbers, you see, because the numbers, they don't really mean much, but here, you can see which part of the cipher it's actually looking at. You see that part, it's not really looking at it there, because that's the output bits there, and it's actually starting at the very beginning. So it's actually guessing the bits at the beginning of the thing, goes all the way down to the very output, doesn't work out, so it goes back, and does this recursively non-stop. Okay. This is, by the way, done by Vegard Nossum. He's an awesome guy. He can code extreme